Professional astronomers have big fancy toys like these to play with when they search the universe. But if all you have is a little telescope like this, it can be pretty difficult to find Halley's Comet or anything else. But there is an easier way using your computer. Today, we'll help you find Halley's Comet and lots of other interesting things in the sky as we take a look at astronomy software on this edition of the Computer Chronicles.
The Computer Chronicles is made possible in part by a grant from AFIPS, the American Federation of Information Processing Societies. AFIPS, sponsors of OAC 86, the nation's leading conference on business technology. For conference information, call 800-OAC-1986. Exploring today's business solutions. Additional funding is provided by McGraw-Hill, publishers of Byte. Byte's detailed technical articles on new hardware, software, and languages cover the latest in microcomputer technology worldwide. Byte, the international standard.
Welcome to the Computer Chronicles. I'm Stuart Chaffee, and this is Gary Kildall. Gary, this is a program called Comet Halley from Great Wave Software, and it helps us find where the comet is in the sky at any one time. You can see there's the comet with its tail right now, right near Sagittarius. I can actually go in here and kind of put it in auto mode, and it'll just click through and show us what the phase of the moon is each day and exactly where the comet is each day, and we can see it moving across the sky there. Gary, it seems there's a high correlation, in fact, between amateur astronomers and computer hobbyists. Were you ever into astronomy?
I was. Well, Stuart, in what seems like a previous life, I taught marine navigation,
right,
where we use tables, logarithms, and a lot of addition and subtraction to come up with a location on the Earth.
20 years ago.
Yeah, it's a long time ago. Yeah, nowadays, with microprocessor technology, you just use a little nav calculator, or if you get really lazy, you just push a button on your satellite receiver.
Today, we're going to take a look at some of the newest astronomy software. We'll meet a professional astronomer to find out how he uses computers, and we'll see real pictures of Halley's Comet. First, we're going to go to an observatory to see how computers have virtually replaced telescopes in the exploration of the universe.
The history of the Lick Observatory near San Jose, California, began in the late 19th century. Its beautiful mountaintop domes were constructed in a wilderness with the help of wagon teams and the simplest machinery. But while the domes still house some of the original equipment, the operation of its telescopes has changed dramatically. The monumental Shane Reflector Telescope is operated by and feeds data to a computer. Its graceful movements through the night sky are orchestrated by a program that determines where to aim it and then compensates for the Earth's movement. The telescope's 10-foot wide mirror is the source of its impressive light-gathering power, but its final output has changed. Instead of an eyepiece or photographic plate, charge-coupled device cameras, or CCDs, can detect levels of brightness with unmatched sensitivity.
I've been working recently taking CCD images on Mount Hamilton. Those, instead of a format of 500 by 500, that means that each image has something like over 2 million separate bits of information in one image. And we might take on the order of 20 or 30 such images over the course of an evening.
Computers have given astronomers greater control to sift through the dense matrix of light points and to analyze objects selectively. With an overlay of false color, objects like the comet appear more prominently. The astronomer positions the telescope remotely by matching a chip's position on the CCD array to absolute coordinates in the sky. The CCD can record bright and faint objects in the same image thanks to its quick exposure time. Finally, astronomers can more easily isolate an object by separating it from the surrounding light emissions and reflections. In fact, to some researchers, the density of information available today taxes our ability to absorb it.
I'm an observational astronomer, so I can speak observationally, and it's meant that taking the data is a factor of 10 or 100 times more efficient today than it was 20 years ago when I first entered the field. In fact, we're almost swamped with data today simply because of the computers.
Joining us now in the studio is Evan Scharf, Chief Astronomer for Scharf Software Systems of Boulder, Colorado. And next to Evan is Robin Raskin, Contributing Editor for Family Computing Magazine, which has just completed a comprehensive survey of astronomical software. Gary?
Robin, it seems like a natural fit to have personal computers and astronomy come together. In your survey, what's really available now?
Well, what's available is very exciting because I first started this survey in 1984. We took a look and we decided there really was nothing available for the novice. It was mostly mathematical tables you were looking at. Nobody understood them. Then came interactive graphics. And the exciting thing that you have now with computers is you have an interactive way to say, show me a constellation, show me a star, show me a planet, and view it graphically on the screen and take that information and then go out to the real world and look up with a little more knowledge. And it's become a very exciting way for novices to learn.
Well, when you talk about novices, are you talking about students mainly, or are they just amateur astronomers that use this?
Students, for one. Amateur astronomers can go further and look at some of the coordinate information and do a lot less of the mathematical interpolation. But families who use their computers for checkbooks and other chores can just sit down for the first time, and especially with the comet here this year. It sort of is very exciting to have a way to learn that is interactive and a family venture. So our family, for one, has become amateur astronomers because of the home computer.
Now, Evan, you have a program called Telstar?
Yes, I do.
As an example of this, so let's take a look at it.
Well, Telstar is a program for someone who knows nothing about astronomy and would like to come out and look up in the sky and find out what's there, what it is, how can I learn about it. Telstar lets you have a location that may be a standard location, in this particular case San Francisco. It could be hometown anywhere. And one can pick a date and time between the years 0 and 3000. For our particular example, we'll pick our standard time in San Francisco, and I happen to like 4 o'clock in the morning, which is standard time.
I don't like 4 o'clock.
Well,
tell us why.
It turns out that 4 o'clock in the morning on March 10th, 1982 was one of the days that was going to be the end of the world. It was the grand conjunction of all the planets. The planets were going to line up, the gravitational forces, the metaphysical forces, and so on, and the world was going to fall apart. But what was so exciting was that it gave an amateur astronomer and people looking in the sky a chance to see 6 planets lined up in a view only 90 degrees wide. And what we're going to do is take the standard information presented on Telstar and let's look at it graphically. The system will be loading, doing various calculations on planets, adjusting for the Earth's precession or wobble, calculating inner and outer planet relationships, and present a view to us that's graphical. The view, as we'll see it in just a few seconds, is 90 degrees wide. We'll start out looking due south and covers from the horizon to directly overhead, or the zenith. There are 9 views within Telstar. 8 of them are 8 points of the compass, with the 9th being directly overhead. And in the view that we have here, we have actually 6 planets lined up. The planets are represented by small circles representing the planets with a ring around Saturn, as well as showing dim stars, bright stars, and constellations. It seems that constellations are one of the most fascinating elements. People read about them, would like to see them, and you stand out there and look up in the sky and end up with a sore neck but haven't really found out the constellations.
Suppose I want to help recognize one of those. What can you do?
What we'll do is merely press C for constellation.
It was easy.
And Telstar will draw the lines between the stars right before your eyes so that you can see the shapes. To identify any object on the screen, one merely presses I for identify and moves the crosshair to an individual object. In this particular case, we'll pick the constellation that's kind of a square right in front of us. And if one has the crosshair centered on the screen, it'll tell us that this particular one,
Constellation Libra.
Constellation Libra. It will tell you the astronomical location, the right ascension and declination, but also the azimuth and elevation, the compass heading, and how high, the time it rises, and the direction in which it rises from, and the time that it sets.
Okay, Evan, suppose I want to find a particular thing ahead of time, and I want to see where is it in the sky.
We would enter a date and time, and by the way, this will cover between the years 0 and 3000 for any location. And we'd enter our date and time, and we merely enter L for locate. In this particular example, let's locate Saturn.
Okay.
and it will give us the same information about Saturn. In this particular case, it tells us the phase or the illuminated portion. After presenting the technical information, our view changes, and there's a flashing crosshair in the middle of the object. There is no doubt.
If we didn't recognize it by the rings, the software would
do it.
Evan, how many different objects do you catalog now in this program?
There are 3 different star tables, and each table has about 250 objects, and they represent the brightest objects that one would see when you walk out and look out with the naked eye.
Okay.
And we could find Halley's Comet, for example, on here if we wanted to use it for that.
If we picked a date and time when Halley's Comet was close by, we certainly could. In fact, I've used this for my viewing on a regular basis to go out and find the comet.
Robin, what does the software approach to astronomy do that you can't get out of a book or the usual list of tables and numbers?
Well, of course, Evan's approach is being graphic and interactive. Not everybody lives near a planetarium. If you do, you probably don't. You live somewhere where there's so much ambient light you can't see the stars anyhow. Evan gives you the best of both worlds. You have an interactive planetarium. Books are static, stars are dynamic. They move. Programs like Evan's Telstar moves. Some other software that's available that does some exciting things to complement Evan's are tutorials. There's one called Journey to the Stars that has a tutorial on apparent motion. You stand on the Earth and you understand why the stars seem like they're moving, where you're moving, and it all begins to make sense. There are bulletin boards for novices who cite their spotting, so if you have a modem and you dial up on some of the networks, you know, a whole new world is opened up there. People are very anxious to share information at any level.
How about in the school systems? Are they being used extensively in schools now?
There are some now filtering into the schools. There's one package called Astronomy that has 10 simulations, and it lets students create the birth of a planet. It lets planets go in their orbits, and it really gives you a visual feeling for what's going on.
Evan, briefly, what do you do about translating the 3-dimensional world into the 2 dimensions of the screen?
Well, it gets to be a little bit of a challenge. Things that are close to the horizon or up to about 45 degrees of elevation look normal, but when one goes to higher elevations, you get a distortion. You can't display a 3-dimensional sphere in a 2-dimensional plane. And so I have an overview which is provided that is looking directly up overhead, and it shows the same information. One can see constellations or identify without the distortion that one realizes up in the upper elevations. It's totally necessary to have both.
Well, that's pretty interesting stuff. Thank you both very much. In just a minute, we'll see a computer's eye view of Halley's Comet, so stay with us.
Until recently, scientists have been confined to observing the stars as a series of snapshots through telescopes. But today's astronomers are now seeing space as a dynamic, moving universe, condensing time, if you will, through computer modeling. At NASA Ames Space Science Research Laboratory in Mountain View, California, astrophysicists are exploring the unseen, employing data gathered from infrared satellites and space probes. The data is entered into sophisticated graphics workstations, manipulated and tabulated through a VAX minicomputer and NASA's Cray supercomputer. The result has been this startling imagery of universes colliding, experiments solidly grounded in physics.
And we can then, out of those interactions, out of those experiments, extract certain characteristic properties that we would expect. We then go back to the observational people and say, this is what we would expect in interacting systems, for instance, or in the formation of an individual galaxy. That's another example, perhaps, is in the formation of an individual galaxy. These numerical experiments tell us that there's very likely these shapes are much more complex, certainly for elliptical galaxies, than we thought in the past.
The modeling experiments have to date proven that halos of matter, invisible through telescopes, exist throughout galaxies. Coming experiments will attempt to explain star formation and how planets are created. NASA Ames researchers continue to pioneer this new kind of astronomy. Says Dr. Smith, it is this interplay between observation and theory which allows us to make progress. For the Computer Chronicles, I'm Wendy Woods.
We're back in the studio now, and joining us is Bob Peterson. Bob is professor of astronomy at the College of Marin, also the founder of Starsoft. And next to Bob is Steve Vogt, associate astronomer at the Lick Observatory, which is headquartered at the University of California in Santa Cruz, near you, Gary.
Okay. Steve, we often have this view of an astronomer sitting out in front of his, peering through his telescope through these lonely nights. Have computers really changed that at all?
Absolutely, Gary. The field of astronomy has been totally revolutionized by computers. We rarely ever even look through our telescopes anymore. Computers are used to control and point the telescope, personal-sized computers. Computers are used to control the electronic instrumentation that is used to actually do the observing for us. They're essentially glorified TV cameras. And the computers, larger computers, are used to reduce and analyze the data and simulate astrophysical situations to model them and see how they agree with our...
Well, Steve, as a professional astronomer, what kind of information do you look for? What kind of things do you collect?
We collect photons, basically. As an optical astronomer, I collect light. We observe photons, we count them, we sort them into their colors or polarizations, and that's essentially our entire medium for understanding what's going on out there.
Hey, Bob, we want to know about Halley's Comet, I guess is what we're getting at. You have some software called Halley. Tell us about it.
Oh, yes. Basically, it's 4 small programs put together. It is very graphic in its orientation, and it's an animated sequence allowing you to see Halley's Comet. It's sort of a God's eye view, an overview from the heliocentric view, as we refer to it as. And I'm going to enter a few numbers here, if I may, for a moment. Start back in October, for example, 1985. We're going to be looking down on the solar system, looking at the sun. We're going to display for approximately 300 days and perhaps look every 5 days or so. We'll tell it that we want to look out to maybe the orbit of Mars. And here's a display. We see the formation of the tail as it begins to approach the perihelion point, the closest point to the sun. Tail rather fully develops and then begins to diminish. That's the first program. Actually, I'm going to rerun.
Can you just make clear what we saw there, Bob? That's the path of the comet for a 300-day period, starting from that date you entered.
October 1st.
And they were the orbits of the planets that were identified on the side there. Okay.
The next one, I'm going to actually start January 1, 1945. This is about the time when the comet is furthest away from the sun. I'm going to run this for a period of 95,000 days. That sounds like a long period, but we're going to only look every year.
This is astronomy. I mean, what's 95,000 days?
Well, it turns out the 95,000 days is roughly the period of the orbit of Pluto, so we can see the complete orbit of Pluto out there. I'm going to select the size here of 50 astronomical units. An astronomical unit's the distance between the sun and the Earth. And we'll go ahead and display that. Here we can see the comet come in very quickly around the sun. That process is basically over at this point, and now we're just seeing actually Pluto completing,
on the outside,
right, completing its orbit. Right. Okay, then we'll switch on.
Okay, that was heliocentric view.
That's heliocentric view. Now we'll move to an Earth-based view or geocentric view. This one allows us to look up at a star map, basically. Again, I'll select the same dates, October 1, 1985. And we'll select 9 o'clock in the evening, 2100 hours. Again, 300 days for the display, and again, 5 days at a time. I think we'd probably like to see the stars out so we can see where the comet is in relationship to the stars. So we'll enter that. Stars are presented on the screen, and then the path of the comet is displayed. And we can see a rather strong tail being formed in that particular display. We have one other way of rerunning that program to allow us to also see the sun's position. Maybe we'll quickly run through that.
That was helping to show us, by the way, that it's pretty low on the horizon up here at this latitude. Huh?
That's true. We're going to be not blessed very well. It would be nice to be in New Zealand for this occurrence, particularly in late March and early in April. Let me quickly...
So you're doing the same thing now, and you're going to also show us the sun's position.
That's correct.
In addition to that.
That's correct. We'll put in 5 days, and yes, we want the stars and the sun. And in this particular view, we'll see actually the occurrence of perihelion, where the comet comes very close to the position of the sun.
Is this software going to go on sale in late March?
Well, it's been on sale for a little longer than that.
Steve, now we've been looking at computer versions of Halley's Comet. Now, I understand with your big stuff down at Lick Observatory, you've actually taken pictures of the comet. I think we're going to roll that tape now and take a look at it. Could you describe for us what it is we're seeing?
Sure. This is a computerized image-intensified version of one night's worth of data on Halley's Comet. This was obtained at Lick Observatory using our 40-inch telescope by Richard Stover and Burt Jones. Each frame was taken with a CCD, or charge-coupled device detector, and then the information was processed in a computer and assembled into a color-enhanced image here. The colors that you see there are not real. They're simply representations of intensity, which is convenient for astronomers to be able to see detail and structure more clearly.
Okay, we're not really seeing, this is not an optical film picture, right? This is really a television picture of the comet.
It's sort of a super television picture with a super sensitive television camera. And that's Halley's Comet in the center there, moving among the field of background
stars. Okay, now what do we have here? You also took this with your system.
Yeah, this is what's called a Doppler image of the star HR 1099, which is really a binary system. This star is about 700 trillion miles away, or about 116 light years. It's so far away that you couldn't see it as a distinct, physically separated star system. It would only appear to be a point of light. And using a variety of computerized techniques, we've figured out a way to make Doppler images of the surface of the star so that we can see these large, dark regions which appear to be on the surface of the star. They're star spots, we call them. And we use the information in the spectrum below to derive the image of the star that you see before you.
What is the graph showing us on the bottom of that picture, Steve?
That's a spectral line profile, or the light of the star at a wavelength that's very near the resonance absorption of one atom, basically.
Steve, that's pretty impressive stuff. We hear a lot about using computers to search for radio waves in space and the search for life and these kinds of things. What role are computers playing there?
Well, one of the biggest efforts that is now underway is the SETI program, where they're using very sophisticated hardware and computers, software, to scan the radio frequency spectrum for signals from intelligent life out in space. They can scan millions of channels at once now using the new high-speed computer systems.
And what kinds of things we've been talking PCs pretty much so far. What are the kinds of things you need a Cray to do in terms of an astronomer's work?
Well, problems like Doppler imaging that I just showed you are that sort of class. You need a much larger machine like a VAX.
What computer, in fact, were you using for that?
We were using a VAX 11780 for that, which is reasonably well suited to it. But the larger the computer, the better we could do the problem. Crays are generally used for simulations where you're making a model of something like the inside of a star or the exploding of a supernova, where you have billions and billions of calculations that you have to perform in order to get the answer out. Very calculation-intensive type modeling.
Bob, we have about a half a minute left as an astronomy professor. Do you find a lot of interest in astronomy and these kinds of things these days, I would think?
Particularly because of the event of Halley's Comet returning. There's been a great deal of interest in the media, of course, and in the general public. So we find quite a bit of activity at the college as a result.
Gentlemen, very fascinating. We're out of time. Thank you so much. We'll be back in just a minute with this week's Computer News. In the Random Access file this week, Computerland is going into the computer business. The company said it's looking for a company in Asia to manufacture a computer to be sold under the Computerland brand name. The Computerland computer would be a low-priced MS-DOS machine designed to compete with the Tandy 1000 and the leading-edge Model D. The new machines could be on the shelf by June. It looks like it's all over finally for Osborne Computers. The company, which had been reorganized after a bankruptcy, is again bankrupt, and its assets will be liquidated. Osborne creditors declared it in default this month when the company could not make payment on a $6 million debt. Commodore posted a whopping $53 million loss for the last quarter, despite near-record sales of over $300 million. Commodore stock has been taking a beating, but some analysts are saying chances are looking good for eventual profitability. Steve Jobs has gone into yet another new business. He just bought Pixar, a company which makes a high-end graphics computer. Pixar had been created by filmmaker George Lucas. The price was in the several millions of dollars. Pixar computers were designed to do 3D graphics for movies, but have found a better market in the medical and military fields. IBM was in the odd role of new kid on the block at the recent Unix show in Anaheim, California. With the new IBM PC RT, IBM is in the Unix game at last, and other Unix vendors seem to be moving toward IBM, with much talk about the need for Unix to integrate into the MS-DOS world rather than stand alone. Time for this week's software review, and here's Paul Schindler.
Imagine being able to find any chapter you wanted in any of these books. A difficult task, right? Now imagine me trying to keep track of 700 files in 20 catalogs on 30 megabytes of hard disk. Housekeeping is one of my most irritating chores. Now finally imagine, if you can, how happy I was to be introduced to 411, a package which indexes everything in every text on your hard disk in just a megabyte or two of space. Incredible? That's what I said. Then I said I was sure it would be too slow to be useful. But, as we say in television, seeing is believing. We'll just give a brief demonstration here. You give 411 a word contained in some file you think is on the disk, and it comes back with the name of every file that contains that word. It can even link you into your word processor so you can start work on it right now. What about all your existing files? You can batch them up and throw them in. What about indexing as you go along? That's just what 411 is all about, with a quick little file called Filet to assist you. Now, I don't think any hard disk user can survive without a copy of 411, $149 from Select Information Systems, Kentfield, California. For the Computer Chronicles, I'm Paul Schindler.
There are some 14,000 companies in the software business, but new industry figures show that 10 companies account for 70% of the business. Here are the software top 10 in order of market share. The top 20 programs, by the way, account for 80% of the software business. In our legislative update file, the budget which President Reagan just sent to Congress includes a surprisingly high amount of money for high technology. Despite budget cuts elsewhere, the Reagan budget for basic research is up 8% over last year. Northwest Airlines has just purchased a $40,000 software package that tells Northwest's Sperry computer how many discount seats it should sell on a flight. The program analyzes 30 criteria, such as load factor and competition, and then it sets the number of cheapy seats. Airline officials said the upgrade of one discount seat a day per flight could generate an extra $12 million a year in revenue. Finally, the story of the $2 billion computer error. Workers at the Federal Reserve Bank in San Francisco spent 3 days learning how to use their new computer system using a dummy program and fake transactions. Then on Monday, the computer went into operation for real. Only somebody forgot to delete the dummy program. So the first thing the computer did on Monday morning was to transfer $2 billion worth of funds to 19 banks which had never requested the money. The error was discovered in a few hours. However, 2 of the banks waited 24 hours before notifying the feds of the computer's mistaken generosity. That's it for this week's Chronicles. We'll see you next time.
The Computer Chronicles is made possible in part by a grant from AFIPS, the American Federation of Information Processing Societies. AFIPS, sponsors of OAC 86, the nation's leading conference on business technology. For conference information, call 800-OAC-1986. Exploring today's business solutions. Additional funding is provided by McGraw-Hill, publishers of Byte. Byte's detailed technical articles on new hardware, software, and languages cover the latest in microcomputer technology worldwide. Byte, the international standard.